Well, good morning everybody. I'm afraid this video is going to be another of my kind of cock-up videos, because what I managed to do is delete half of the footage of assembling what is an audio test dummy load. So what I'm doing here is I'm just designing the cutouts that are going to be in the front panel for the controls. What I'm doing at the moment is I'm just designing the phono outputs. Now this dummy load, it's going to have an output level which can drive the audio input of a sound card, because what I hope to be using is some PC based instrumentation to do some automated measurements on our amplifier. But you can't just output, I don't know, 15 volts from your amplifier into a 2-volt input of your sound card, because you'll blow it up. So what this box will consist of is some large 4 and 8 ohm resistors, which are going to be the dummy load, and also an attenuator network to reduce the voltage down to something that the sound card can cope with. And also there's going to be some clamping diodes in there, so that if we do exceed I don't know, 2 volts, which is what the inputs are rated for the sound card, the diodes will clamp and just limit the voltage to a level which isn't going to cause any damage. So back to what I'm doing on the screen there. That's one of the back cutouts, and I've drawn everything up in AutoCAD because that's what I'm most familiar with. That's what I use quite a lot at work, and I draw up all the various cutouts and everything that I need, and then what I'm going to do is I'm going to print them off at a 1:1 scale on sheets of paper, and we'll glue those sheets of paper onto the various front panels and stuff like that, and we'll use it as a drilling template. Because I don't know about your printer, but the laser printer that I happen to have, I don't think it's a particularly expensive one, but it's certainly an old one, and I found that if I use this transfer method of actually allowing the to draw up all to produce a template, I actually get a much better result than trying to actually just measure anything with measuring tools on the piece of metalwork itself, because yeah, that just shows how good I am with rulers and scribers and all that lot. So basically, I'm sure people who are really accurate and used to using machine and equipment can do a more accurate job than this. But what I'm trying to say is this is accurate enough for most applications that I use. So I've printed them all out there, and I'm just going to glue this piece of paper to a piece of metalwork using just some self-adhesive sticky tape. Looks like I'm feeling a bit posh and using Kapton tape. That must have been what I had came to hand in the desk, but it's a nice pretty bright orange colour, so you can see what I'm doing. So yeah, we're just going to stick the paper template onto the piece of metal using the Kapton. And I can just tell that piece of metal there, that's going to be the back panel of the piece of test gear. And I'm just securing all 4 sides of that so it doesn't move around. And that's the back panel template completed, and I'm going to do the same for all the other panels that need to be cut out. Now that's the back panel there, which is going to have a big slot in it to take a heat sink. Okay, and I've now moved into the workshop, and now we've got the paper templates fixed onto the various bits of metalwork. We're just going to use a punch now, and we're going to transfer the marks from the paper template onto the metalwork using a centre punch. Now I don't know if you can see there the hammer that I'm using looks a bit funky. Well, that's actually a copper-faced hammer, which basically it's got a soft face on it. If you use a normal hammer on a chisel, or centre punch like that, you'll tend to find that the actual hammer, when it blows, it bounces slightly, so that actually reduces the energy that you transfer into the punch, and it also can make like a double bounce, which can actually create two little holes, and they're not necessarily in the same place. So if you use either a brass hammer or a copper face hammer, as I'm using, it delivers what they call a dead blow, and that means that all the energy will go through the hammer into your centre punch and eventually produce a very tight little pot mark in the piece of metalwork. So we're back on the top cover now, and I'm just marking out some of the holes that we'll use to fix the heatsink down onto the top cover. But we're actually going to be milling away most of that top cover in a moment. And we've got the bandsaw switched on there. Not doing anything very exciting here. I just want some pieces of scrap wood just to use on the milling machine table, and also on the milling machine clamps, so that when we clamp the workpiece down, we don't scratch anything, because some of the panels are bright aluminium, and some of the panels have like a manufactured from mild steel, and they're already painted in an enamel finish, which is actually quite brittle and easy to scratch. So we're just putting some pieces of wood as packers there under the clamps to stop us scratching the workpiece. Okay, I'm just kind of tramming the workpiece there on the bed of the milling machine. I just want to make sure that it's the workpiece has been clamped in line with the travel of the bed. And okay, I'm just centre drilling the holes that we're going to be putting in, and that's the first hole. And I can see I've had a bit of a problem there. The milling machine won't go deep enough because I obviously had the depth stop not set correctly. And yeah, I always recommend you use a depth stop on any type of machining operations if you've got one, because there's nothing worse, nothing annoys me more than using machines that have got holes drilled all over the beds because somebody was too clumsy to set the depth stop. It just makes a mess. So yeah, you use the depth stop. It avoids drilling holes in the bed of your milling machine or your drill table, whatever you're using. Now there is a lot of advantages to using a center drill, because if you were just to use a normal small drill, what you will find is a long small drill is quite wobbly, whereas a center drill is short and very rigid, so it will tend not to wander in the same way that just a normal small shank drill will. A small diameter drill, it's just so feeble and weak it tends to bend and wobble around, so use a short stubby center drill and that'll put a very precise hole exactly where you want it. And it's also got chamfers around the edges which help to guide the nose of the drill in. Having said all that about accuracy, I'm probably using one of the least accurate things now. I'm using a cone cutter, and the idea behind these is they've got a series of steps in them, and that one, the cutouts that I'm trying to do are, I think they're about 13 millimeters. So if I had to go from you know, the 2mm centre drill hole up to 13 millimeters, that would be quite a lot of drill stages I'd have to go through. So if you use a cone cutter like this, it will remove quite a lot of metal quite quickly. But they seem to work best in soft metals. As I say, this back cover is actually made in aluminium. The front cover was manufactured from steel, and it did take a little bit more getting through. But these cone cutters are the kind of throwaway devices now. You can buy them on eBay for just a couple of pounds. They tend not to last long, but when you've blunted them, you just throw them away. What we're about to do is we're just going to shortly we're going to mill out the top cover of the enclosure, and so that we can fix the heatsink onto the box. And the resistors are going to be bolted to the top of the heatsink, but they're actually going to be poking through into the box itself so that we can do our connecting wires. So I'm using a fairly small milling cutter there. Now what I'm having to do is a milling cutter has to be held into a milling machine using what they call a drawbar, which is just a long piece of threaded rod. If you've just got a normal chuck in your drill press at home, you probably find that that it will stay in. You just basically ram the Morse taper in and it will grab. But because there's quite a lot of side load, well, it's all side load on a milling cutter, what that will tend to do is if you just have a Morse taper to retain the chuck, it will actually cause the chuck to come out the side load. So if you're using a milling machine, you do need to retain the chuck, and that's done by a drawbar. I'm winding the milling machine head down there because you want to keep everything as rigid as possible, so the closer that the headstock is to the actual workpiece, the better. And I've just plunged the cutter and engaged the automatic feed, which is quite a slow feed because this machine doesn't really have a very high speed setting. So you've got to be a little bit careful when you're actually using small milling cutters. In fact, I actually edited the video here because the first one I put through I was a bit heavy-handed and I managed to snap it off because I didn't have a fast enough spindle speed. So I slowed the cross travel down and increased the spindle speed, and that did a reasonable job. And I've also got a little can of I think it's cutting fluid there. I usually don't bother with anything exotic, I usually just put a little bit of oil or paraffin on, or anything really. Okay, and what I picked up there was the top cover and left a bit of scrap behind. And I'm just tapping out some holes there for the to mount the heatsink. Okay, so that's all the stuff done in the workshop, so let's hand you back to the idiot in the lab who's just going to wire it up now. Using all the heat rubbing some bits of wires and crocodile clips that I've been using previously. I just thought that might be a much more preferable solution to shorting the output of the amplifier out at some point accidentally. I can hear all the chickens singing outside, so I guess one of them must have laid an egg. It's funny when one of them chickens does lay an egg, they seem to be really quite proud about the I don't know if they're proud or it's just a relief to have actually got the egg out, but they do seem to make a bit of a song and dance out of it afterwards. Just to give you a quick run through of what we've got, basically you can connect the output to the amplifier to connectors at the front or the back. I'll probably use the back connectors for most of the things I do, but because I've actually just brought the wiring straight through to the front, it does mean that I can always use these sets of connectors on the front to plug in some additional test gear, like a voltmeter or maybe the distortion analyzer or something like that. And we've also got the raw output as well, just output there onto the BNC connectors. Now, all the wiring that we've got in here, it's effectively isolated. The left and the right side are isolated from each other, and they're also isolated from ground. So the BNC connectors that I'm using, they are the isolated type as well. And so we've got a BNC connector for the left channel, and we've also got a BNC connector for the right. And I guess all will be good, that isolation will be maintained, and unless I do something like plug both of these in together into the two channels of a scope, for example, that would end up bridging the isolation. And I think I commented on some of my other videos, most of the time that won't matter, the fact that it's not isolated or you bridge it out. But there is certain types of amplifiers, which is probably the more modern ones, than the higher output power amplifiers that use a bridge configuration, and they probably don't like having their outputs shorted to ground or connected together. So yeah, you've got to be a little bit aware of what you're plugging in. So the from the input from the amplifier, from the output from the amplifier, we've got these dummy load resistors which are representing the speaker loads, and they're bolted to this quite substantial heatsink that we've got there. And I've also added a switch on here, and what this switch allows us to do, we can switch from 4 ohms, from the 4 ohm position to the 8 ohm position. I suspect most of the time we'll be using this in the 8 ohm position, but it's useful to be able to switch between the two, because if you can switch between the two load impedances and measure the voltage, what that'll enable you to do is do a little calculation, and from that you can calculate the output impedance of the amplifier itself. And with that in mind, I've used relatively thick cabling. I say relatively thick cabling, it's not thick compared with what some of the audio people are into, but this is, off the top of my head, I think this is 2.5 mil square. It might be 1.5, I think it's 2.5 that actually. It's pretty thick stuff. And what that'll allow me to do is just to minimise any volt drops between any of the connectors and between the dummy load resistors. So there's no point in doing all your calculations based on an 8 ohm load if you've actually got 1 ohm of resistance in your connecting cabling. Although we could probably null that out within the calculation as long as we know what that is. And at some point in the future we'll probably do some testing on this just to check how good these loads actually are. The resistors themselves are pretty cheap and nasty things that come from China, and when I did again a quick and dirty test, there is a little bit of inductance on these. They're certainly more inductive than the large ceramic resistors that I was using previously, but yeah, they're in a much smaller package, and for the amount of testing that I'm going to be doing, I think this is just going to be much more convenient. I think if I do build more and more of these, if I do more of these amplifier projects in the future, maybe I will build a bigger version using the bigger, larger ceramic load resistors that you saw previously. But I think these are going to be good enough for what I'm doing. And again, it's not like I'm really interested in ultimate precision. I'm just after doing quick and dirty measurements. It doesn't have to be perfect. So there's not much left to do now. Oh, I didn't really mention this, did I? So what this board is here is one of the main reasons for building this box is that I actually wanted to be able to do some automated testing using a sound card on the computer, but you can't obviously you can't feed 15-20 volts from your amplifier output directly into the line input of a sound card, which has got a maximum of 2 volts. So you need to attenuate that down. So this doesn't really do anything particularly exciting. All we've got here is we've got a resistive divider, and then that is output via a current limiting resistor here, which is 1 kilo, and that goes into these back-to-back Xenodiodes, which are really just being used as a limiter circuit. So if we put a much higher voltage in than the sound card can accept, even bigger than the attenuation of these resistors, what these Xenodiodes will start to conduct, and they'll just clip the top of the waveform off and maintain it at a level that hopefully won't damage the sound card. And both sides of the circuit are symmetrical, so it's built just the same. Now, this was built on Veriboard strip board, and the strips are running down like that. And the strips that I'm not using, what I've actually done them is to link them all to ground. So we've got a bit of we've got a ground connection at either side, and then the middle strips that we're not using, we've grounded them out. And the idea is I just wanted to create a little bit of a gap between the left and the right channels, even though they're pretty close. Everything's built using normal multi-core cable. I haven't used any screen cabling because I kind of considered if you've got a few feet of cabling coming out your amplifier, there's probably not a lot of point in using coax and screen cables inside here. I did consider just screening the output from the attenuator, because obviously this is going to be only a volt as opposed to 15 volts. But in the end I just decided it's a short link and it's going to be in a steel box which is going to be grounded anyway, so I won't bother doing that. And again, I couldn't get isolated phono connectors, so what I did earlier, and I think I maybe showed that in the mechanical part of the video, is I've mounted both these phono connectors on a piece of plastic, so they're isolated from each other and they're also isolated from the metal body. So I think all I need to do now is just screw it together, maybe just make a label for the front of it. And this is a little bit tight. It's not going together. For some reason it doesn't seem to be quite going together. I've got some wiring trapped under there. Okay, put them screws in loosely to stop everything falling apart. Oh, I have to say, basically, if we want to, we can actually ground the metal enclosure. And you can see I've used a relatively substantial heatsink here. This is just one I had lying about. It's actually, I was going to say that, I think I picked this heatsink up at a radio rally for kind of like 50 pence or something. And I don't know if you've had a look recently, but the cost of heatsinks is really, they're quite expensive items, even to buy on eBay. So it is worth you know, looking out for heat sinks for projects. If you see one going cheap, you know, buy it, because you know, substantial pieces of ironmongery, a big piece of aluminium, the price of this stuff's going up. So all we've got to do now is put the 4 ohm, 8 ohm switch in, and hopefully it will fit. It looks like it's a bit of a tight fit, and then we've done. Actually, that does feel a very tight fit. I wonder if we can mount that. Well, I might have to mount that switch sideways. These switches are always buggers to mount. Again, I've used quite heavy switches based on that's what I've managed to find lying around in the junk box. But I don't know how I'm actually going to tighten these up at the back. Because you need a very slim spanner. I don't actually think I've got one. But it's designed to go like that. So I think what we'll have to do is we'll have to put the 4 ohm side there, an 8 ohm there, and we're going to have to see if we can find a spanner which will go in there. I wonder if my adjustable will go in there. It might do. Again, it might be, no, it won't. Yeah, I need something thin to go in there. I'll have to go in the garage later and see if we can find a box spanner that'll fit. And yeah, it's going to have to be quite a thin spanner. Can I just get something in there temporarily? And I better just check those these BNC output connectors. So. All looking good to me. And the phonos. Well, that's looking fairly good to me as well. Let's just check the earth connections. A little bit of scraped off paint there on the case. Let's try that. And front to back. Right, okay, so everything that is earthed is earthed. Everything which should be floating is floating. And just for the record, we might as well just get a measure of the inductance using this peak analyzer LCR45. So that's telling us that we have 7.91 ohms, 7.91 ohms, and our inductance is flicking around a little bit, 1.99 microhenries. Let's call it 2 microhenries. 2.00 microhenries. And if we just flick the switch to the 4 ohm setting, we would expect the inductance to go down. And in fact, that's one of the quite useful reasons why it's often an idea when you're making dummy loads, rather than use the resistance value that you want, to actually use multiple resistors in parallel, because it does bring down the inductance. So let's flick that to the 4 ohm setting, switch on again, and we should have a low reading. And yeah, let's call it approximately half. So again, we've got we've got 4.08 ohms, 4.08 ohms, and we've got an inductance of 1.24 microhenries. 1.24 microhenries. Good. I love it when a plan comes together.